This video, I will talk about our group selected paper scalable diffusion models with transformers. This paper explores a new approach to diffusion models for image generation by replacing the traditional neural architecture with a transformer-based model called DIT. To start, diffusion models have recently become a leading method for generating high-quality images, but most of these models rely on the UNet architecture as a backbone. The main challenge addressed in this paper is improving the scalability and efficiency of the diffusion models. They also propose using transformers instead of the UNet, aiming for better performance as the model size increases. This shift is significant because transformers have already shown success in other fields like NLP and CV. Applying them here could unify architecture design across different domains. Let's take a closer look at the two architectures used in the diffusion models, the traditional UNet and the new proposed DIT. On the top, we have the UNet architecture. UNet is a convolutional encoder-decoder model that was first introduced for biomedical image segmentation but has since become the backbone for many generative models. The input image passes through a series of downsampling layers. These are convolutional layers that extract increasingly abstract features. At the bottleneck, the network starts to upsample, restoring the spatial resolution of the input image and skip connections between the encoder and decoder, help preserve spatial details, ensuring a better image generation quality. However, this convolutional architecture has limitations in terms of the scalability and efficiency, particularly as we try to increase the model size and complexity. On the bottom, we have our DIT. Unlike UNet, which operates in pixel space using the convolutional layers, DIT works in latent space and uses transformer models self-attention mechanism. Here we can see the more detailed DIT architecture. The key difference here is that input image is first compressed into the latent patches. So instead of processing the whole image, we will working with the smaller, more efficient representations. The latent patches are passed through a series of transformer blocks, each with a multi-head self-attention and feed-forward layers, which allows the model to capture complex, long-range dependencies between the different parts of the image. So we can see DIT leverage the scalability of the transformer, and by operating on smaller latent patches using the attention mechanism, it can handle much larger and more complex models without significantly using computational costs. Let's look at the results here. One key matrix used in the generative models is FID score, which measures the quality of the generated images. The lower, the better. So we can see the DIT XL over 2 models with the 118.6 G-flops achieves a state-of-art FID score of 2.27 on the ImageNet 256 times 256 benchmark. This significantly outperforms the previous UNet-based models, demonstrating the diffusion models can scale more effectively. And as you can see, larger models like DIT XL over 2 and DIT L over 2, which are shown in blue and green, perform much better over time compared to the smaller models such as DIT-S and DIT-B. All models improving as the training steps increase, but the larger models scale much more effectively. For instance, DIT XL achieves significantly better FID scores as it's trained for more steps. And at the bottom, we can also see the model comparison table. This table has the DIT-S, DIT-B, DIT-L, and DIT-XL. DIT-S is the smallest model with 12 layers, a hidden size of 384, and it uses 6 attention heads. It only requires 1.4 G-flops, making it more computationally efficient. but it doesn't perform as well as the large models in terms of FID. On the other hand, we have the largest model, DIT-XL, which has 28 layers, a hidden size of the 1152, and uses 16 attention heads. It requires 29 point G flops, but as we saw from the FID graph, it also achieves the best image generation. So we can see the larger models like DIT-L and DIT-XL require more computational resources, but they deliver superior performance in generating high-quality images, especially when trained for a larger number of steps. This underscores the scalability of the DIT architecture. The more compute you have, the better performance you have. In conclusion, this paper introduced DIT, a scalable and efficient alternative to the U-Net backbone in diffusion model for the image generation. By replacing U-Net with the transformers, the authors show that we can leverage the scaling properties of the transformers to achieve state-of-the-art image generation performance. This development could open the door for more unified architecture across different domains like NLP, CV, and generating models, making future models more efficient and robust.